Test, test. Oh, nice. Hi, everyone. We'll get started in, let's say, 30 seconds. Nicolo is here, excited, ready to go. I know there's a few more people outside, Nicolo. I don't want to distract you, so we'll give him. I'm counting in my head. Damon, is there more people outside? Okay. All right. Hello, everyone, again. 2 more sessions, pretty interesting ones. Nicolo will join us and talk about multimodality with vLLM, so vLLM-Omni, pretty awesome project. And then Michael will come back on stage and cover how do we do vLLM with Kubernetes with llm-d. He briefly mentioned that in the earlier presentation, but he'll do a little bit of a deep dive. So with that, remember the survey afterwards. You'll hear from me after Nicolo and Michael, but with that, I'll pass it to Nicolo. Welcome.
Thanks, Sasha. Hey. Okay. Hi, everyone. I'm Nicola. I'm a senior ML engineer with RedHat, and I also serve as a maintainer to the vLLM project. And so it's my first time here in Poland, and first time I'm also delivering another first time is me giving this talk about vLLM-Omni, which is a very, very recent project that joins the vLLM ecosystem. And And to get started, to introduce vLLM is quite easy. Basically, vLLM-Omni is extending vLLM multimodality support from just input to also output. So being able to like generate images, videos, audio, and so on. And it does so by leveraging, obviously, what vLLM already offers out of the box, which is the efficient autoregressive transformers inference, and adding a core piece to the picture, which is that of obviously running diffusion models. And we'll see later how that fits into the Omni architecture. So let's get right into like hands-on experience. What it offers out of the box is very close to what everyone is used to work with in vLLM. So first of all, there's an offline API, so a way to just use Omni as a regular Python library. So it is mostly useful for your offline workloads, so your batched workloads. And then you can also use it, of course, as a fully fledged server. So you spin up a fast API server, and what you get out of the box is basically, again, OpenAI API compliancy. So most importantly here, I just want to highlight that you can still use the chat completions API for multimodal supports that you may have already used with vLLM. But it's obviously extending that with like a new set of APIs. For instance, the images generations one is the one that got popularized with DALL-E model from OpenAI, and so this is and a lot more endpoints are available, of course, out of the box in Omni. And what can you do with these many endpoints? Basically, you can attach a UI to it, so you can use the client of your choice. It shouldn't come as a surprise. vLLM-Omni doesn't like enforce itself the choice of like any particular client. Of course, in this picture, I'm just showing you one from vLLM Playground, and basically some of the like tasks that are like quite popular, especially for like local deployment, for like experimenting with your model locally, might just be like generating obviously images, but also like doing things like style transfer or in painting, or just editing images like with textual prompt. And we'll see later how that fits into the design of the diffusion engine, basically. And then again, especially with the new release of like Qwen 3 ASR, it got very popular to like generate voices, but also to clone voices. So I think you should give it a try. It's actually quite impressive. It also it comes out of the box with an integration with Comfy UI. So if you want to really take that client experience like to the next level, you can try Comfy UI. It's basically a way for you to just create a workflow on a with a like graph-based system, so you can define nodes, and it's particularly useful when basically your pipeline gets more complex. Now, getting a bit into the design of Omni. So Omni is just not for diffusion, so I don't want to give that idea. It's actually more for one may think about like an orchestration of hybrid multi-stage pipelines. When I mean hybrid, I mean pipelines that are made of autoregressive transformers and also like diffusion models. We'll see later some of the taxonomy that are involved. But from the design perspective, Omni basically chooses to have a very, very flexible interface, which is that of a stage. Stage, you might think it as a node in a pipeline, and it doesn't enforce like any like particular design, but it will basically the taxonomy of this stage is that it can either be a like diffusion stage or an LLM stage. LLM stage, the one on the right side, will obviously fall back into the vLLM mechanism that we've seen earlier, while the diffusion side on the left side will use the diffusion engine, which is sort of like one of the core novelties of Omni. There's a separate scheduler, so something I just want to mention. So if you're in a pipeline, obviously you're already in part of the pipeline where you're on the AR side, you're using LLM scheduler with minor modifications, while on the diffusion side, the scheduler is currently like very it is very straightforward. It doesn't do any like continuous batching. It will basically just take single request and generate the diffusion output. Yeah. So on the so what we're seeing here is the stage, which is like from the developer interface, and then basically you can extend that all the way to the end user interface. And this is very similar to vLLM if you're used to it. Basically, you will have an asynchronous version that obviously you will most definitely need when spinning up the server, but you also have a synchronous version, which is more important for when running offline. And these are like the two entry points that you can use. Obviously, the entry points Omni for synchronous offline mode, an API server, which is also kind of swappable. I mean, you can use another OpenAI compatible API server, but this is not something that usually people do aside from like a working group working on maybe replacing the API server with something like more performant like Rest. But let's not get carried out here. So yeah, so basically we've seen how vLLM-Omni defines a pipeline. So the first thing that might come to your mind is how you basically scheduling these pipelines. So pipelines usually you will have, if you do it naively, you will find yourself in situations where you're having these so-called bubbles. Basically, if you have like multi-stages, as we talked about earlier, you will find yourself that if stage one is basically going to be locked until the process is the request is processed until the end of the last stage. So this is the case if you're using the Hugging Face Transformers library, which is sort of like what Omni compared to when it got out as a baseline. So what Omni does, as we are doing in vLLM as well, with things like pipeline parallelism, is basically to allow the request to flow through asynchronously. So basically, you can keep all stages, fed and working by just continuing to provide the following request without having to wait for the last stage to be done. And I mean, this goes without further ado, but the the throughput that you gain from this can be like obviously very huge. So I also didn't go too much into the details of like comparing with the baseline, because there's also, you will find of online are mostly based on this like very like single missing piece that the Hugging Face libraries do not have. And now I just want to carry onto that comparison, looking a bit closer to AR and DIT. In particular, again, AR, think about like what vLLM offers. Usually, what I would like to highlight here is obviously the bottleneck in terms of computation. When serving a regular LLM model, we usually separate into like prefill and decode, with prefill like just filling the KV cache and decode being the generation step. Those two kind of steps are like, those two kind of stages are like very different in terms of computation pattern. And we see that basically prefill, we say that it's compute bound, while your generation, your memory bound. Moving to diffusion models, this is actually much simpler. So in theory, you're always like compute bound, given obviously the limits and the availability of your hardware, which actually makes a lot of things easier. You don't have that, at least within the single diffusion transformer model, you don't have that intrinsic, computational pattern shift as the model generates more tokens. So it's a lot simpler to serve under that regard. And there's obviously also no KV cache. There are kinds of caches that we might touch upon later, but these are not like they're not perfect caching. It's more like caching different steps of the diffusion process by similarity. This is the taxonomy of models that you may come across in wild. So basically, probably want to start from the one in the middle, which is the one that maybe some of you already have seen. This is the akin to what Quen image does. Basically, you have a core transformer, diffusion transformer model that is generating the image, while the text embedding is produced by, in this case, like Quen 2.5 VL. In this setup, we have that the autoregressive model is actually like a minor part, if you want. It's just like basically taking the prompt as input, generating the embeddings from the prompt, and then those embeddings are fed into the DIT, which will carry on that diffusion steps and time. And similarly, the patchify is basically a straight highway for the input, either image or noise, to go into the diffusion model. While a more elaborate model, such as the Quen Omni style, basically will have a more elaborate way in which we have a two-stage pipeline for both like the so-called thinker and talker, which these are like autoregressive. It's a single autoregressive model that will do two separate stages, and then those will finally feed into the diffusion head, which is that it's producing sound waves. So it's basically producing the speech as in output. Yeah, so going into how can you shard some of these models when you have a multiple GPUs obviously. I think this is the number of parallelism that vLLM-Omni currently implements. It's especially interesting to look at from the diffusion perspective. From the AR perspective, again, vLLM takes care of all of that. From the diffusion perspective, we can see like also shift in nomenclature. You have sequence parallelism. Sequence parallelism, we might maybe know it by context parallel. Basically, you have a sequence. A sequence is sharded in the time dimension, basically, so across the sequence, and the the different devices will only compute a portion of the attention, and then there's obviously collectives to make sure that both devices get the full attention score as they go through. I think it's a Wi-Fi. Okay. And then other tensor parallelism, I think we're already covered with Michael, but another thing I just want to mention is the just the merge VAE patch parallelism. Basically, you're able to, when you're doing the VAE, we'll see later, decoding step, you're able to like tile the upsampling stage and to do it in different GPUs and then merge it all together at once in the end. As well as the CFG parallel. These are like options of parallelism that you don't have when you serve a regular LLM model. Because, for instance, here you can split the positive and negative prompt. You can split it and run it into like completely in parallel into separate devices. And obviously, this is a peculiarity of diffusion models that you can't leverage in vLLM. So, yeah, speaking of diffusion models, if you, like me, have to like get up to speed with diffusion, and you maybe come to it back from when stable diffusion was released, it may look like this. So basically, the core framework, I want to also, hopefully this is encouraging, is still the same. So we still have a, if we go from the top left onward, we still have a input image that goes through a VAE encoder that produces basically a latent representation of your input image. Input image is usually either like conditioning for your model, if you like doing things like style transfer or so on, or if you're just generating from prompt, that is just pure noise. And then the diffusion process is the big block in the middle, which back in the days, like 4 years ago, used to be a UNet. Now we basically replaced it with the DIT in like newer architectures such as QuantImage. And then what happens in that UNet and our transform model is that there's a cross attention mechanism, or anyways, a way to basically take the text prompt, embed it, and then feed that embedding into the model to basically guide the diffusion step and the generation. Yeah, so we're almost out of storage. Yeah, this is exactly what I was referring to with the QuantImage. This is basically the same picture, but this as of today, let's say. Here, I probably want to mention again. There's a text prop. It gets split into it gets embedded using Quen 2.5 VL, and then there's a VAE encoder which follows a patchify. These are all ways to basically get your input and basically project it into token space, where this is the input to the actual transformer, and the transformer will repeat the diffusion step n times, as it happened with UNet a few years ago. Yeah, and then in the end, obviously, there's an unpatchify step, which is a peculiarity of transformers model, where you have all the output tokens generated, and then you just reshape them back into an image. Yeah, sorry, I think. Okay. So how does this reflect into the framework? If you take a look at the design from perspective in terms of like the diffusion engine itself, we've talked about the scheduler, that's okay, but the diffusion worker is really like the core of the engine. Here we have the 3 stages that we have elaborated on earlier, but I really want to bring up that there's an acceleration layer, which is kind of should be like the shared utils that Omni offers to out of the box, basically make sure that your model is running as fast as possible. Some of those optimization include, they put that in, obviously, torch compile, which is a big feature for vLLM itself, and we're trying to do the same here in Omni. in Omni, you will find yourself not compiling the whole thing, but actually what happens is that you're defining blocks of compilation. Usually it's the DAT transformer block that you can more easily compile, and that's even more important because if you think about like one generation step, you usually do it like 50 times. So those just compiling like a single transformer block brings in a lot of benefit here. There's the same attention backends mechanism that like vLLM does, has different ways of computing the attention. Omni wants to do the same, so not flash attention, just not like torch SDPA out of the box, but backends that really push your accelerator to the limits and also tied to your specifics of your hardware. And then there's caching, which I mentioned earlier. It doesn't happen. It's not perfect caching like KV cache that you might be used to, but it's more like these T cache or DB cache are additional ways to basically try to skip computation when between one inference step and one diffusion step and another, you're able to like recognize that the change is minimal between below a certain threshold, and so basically we'll just skip that particular diffusion step. And in terms of like code, how do you implement a diffusion model? It's basically currently a lot of it you will find that it's mostly what happens with the diffusers library. Actually, you will find the same tree in terms of like code in Omni, and we've actually went through this pipeline many times already in this talk now. So I just want to highlight that other than the text from encoding, this part here is what it's currently being abstracted away, but more work will be ongoing to actually try and abstract more things and make it shared, so that when you had a new model, you don't have to re-implement, for instance, like the encoding, which is currently like there's no abstraction. You just have to redo it for every model. And now finally, I just want to share like a very quick out-of-the-box comparison, since I know that some of you will actually ask about it, so I took the occasion to just do it myself. Like big disclaimer, these are like obviously like very take the results with a grain of salt. I just took SGLang diffusion, took a vLLM-Omni, ran them on an H100 without like without tuning parameters of the server at all. This is really what you get when you just do UV pip install vLLM-Omni. And what I wanted to highlight that I couldn't. Some models are obviously not supported on both, which is the case for Bagel, which I only could run on Omni. And again, there's no clear win here. We have Quen image that's running much faster on this Pareto chart here. So sorry, I should have. So we got like throughput on the y-axis and the latency on the x-axis. You obviously want to have you want to go as top left as possible here. So highest throughput and minimal latency, and that's the case for Quen image, for Omni, while on the Flux case, especially at TP8, we see SGLang still working a bit better at that. And this is the same data, but like charts, so maybe it's easier to see the difference. And yeah, and so that's really all I had in store for you today. So thanks a lot for the attention. So I'll hand it over to Michael again.
Hello again, everyone. Thanks to Nicolo for vLLM-Omni. Today, I will be now covering llm-d, the distributed inference future. So llm-d is a library, built natively with Kubernetes in mind to manage and operationalize your many vLLM deployments you probably have, both for different models, but also for single models as you scale across different hardware platforms, or scale your models to running across nodes and nodes of accelerators, as I sort of mentioned earlier. So it's important to realize that llm-d is on top of the inference engine, the inference server, the models, and handling really the routing and management of all of your LLM serving instances. As we've already covered, vLLM de facto inference standard. That's why we chose it, and that's the focus of llm-d and why it's built hand in hand with vLLM. Yeah, why llm-d? Like, why do you need ultimately like something to manage vLLM? This is because managing, like, if you think of vLLM as like an HTTP server, like a web server, you need to manage it quite a bit differently in how you're scaling up your servers and routing between all of your different web servers. In the world of HTTP requests, they're mostly kind of the same size in terms of work and how long they're going to take. But obviously, we know from LLM Inference, the requests we're getting there are very different in terms of whether a request is going to finish in a second or it's going to take minutes. Say if you're running long agentic tool calling, tens of thousands of tokens out of your request. So we actually don't know how long a request is going to take at a given load on a given server. So we need to make sure that the whole router and everything on top of that is aware of some of these things a bit more so it can properly load balance and route to the right server. So as I mentioned, the core pieces of llm-d or abstractions are vLLM and Kubernetes. And when I say that llm-d is built natively in Kubernetes, it's not just working with Kubernetes and virtualization and Docker. It's also like using things from the Kubernetes ecosystem, like the Envoy, like inference gateway, or the router, inference scheduler. All these things are essentially assembled in what results in like llm-d basically being a Helm chart for like all the pieces of the Kubernetes ecosystem you want to use. And as a result, it's meant to be very hackable and plug and play for all of these different pieces. You can swap out the routing, you can swap out the scheduler, design some quick YAML to change the filtering or routing strategy. And of course, that abstraction also suits well for flexibility across platforms or interconnects, or whether you're on a local like Minikube cluster, or whether you're on like AWS, like scaling across EFA. Yeah. So the key like purpose behind, or the key thing we aim for within llm-d is defining sort of well-lit paths and sort of the reason why you need to start thinking about distributed inference and what are the key use cases that you want to benefit when you're getting to a scale like this. And I'll sort of walk through some of the key paths and how we prove them out. So there's the inference scheduling part, which hopefully makes sense. How you're choosing to route your incoming request, from like the completions API, it goes into the Envoy and communicates with EPP and your different vLLM pods, and we can have different intelligence that we can add in there, whether we want to route based on how much prefix cache percentage like we're hitting on all the different nodes. What would be the place that would get us the best prefix cache hit rate for a given request routed to a given server, or like load aware routing, where we need to scrape metrics constantly from all of these pods and know not just how many requests are running on the vLLM node, but also what's its KV cache utilization. Is it running prefill requests or decode? Is it a prefiller or a decode specialized node? These are sort of there's several like baked in routing policies, but you can of course make your own. And here we have some benchmarks comparing if you're doing simple like round robin style scheduling in the blue line versus taking into account KV cache load and KV cache utilization scores, where sort of lower here is much better intertoken latency, time to first token, and ultimately throughput is I think like 3 times better once we get to a high enough QPS or request rate, once with the sort of better scheduling. And you can customize this as you like. Next, there's PD disaggregation. Hopefully you understood a bit of what I mentioned before about that. But ultimately, we have vLLM pods that are decode nodes, vLLM pods that are prefill nodes. You have your request coming in. It's deciding whether to use prefill, whether to do PD, or maybe it has a really high cache hit rate, and so it should just skip straight to the decode node and do a really small prefill on the decode, because it can skip most of the prefill. But it needs to manage all these points of contact and communication of first routing the request to the prefiller, telling the prefiller that it needs to send to this specific decode pod, preparing the decode pod for that transfer when the prefiller is done, and managing all these things at the millisecond scale. And as I've already mentioned, we handle the KV transfer using the KV connector API in vLLM, and we focus really heavily on the Nixel library as an abstraction over the many different types of interconnects and protocols that we might use. RDMA, we use like UCX. We can talk over InfiniBand, over RockE, over EFA, even over TCP if you are okay with slowness. But ultimately, we're using this abstraction both in vLLM and llm-d to ultimately transfer and manage your KV cache most quickly from device to device. We support ultimately very flexible deployments. So when you're doing disag PD, maybe you want to run your prefill node as like TP1 because you don't actually need that much KV cache space. You just need enough KV cache to fit the one request that you're prefilling, and then you're immediately dumping that KV cache to your decode node. Whereas your decode node, you want to scale it up to a higher parallelism. So you can allow for this heterogeneity and parallelism. This is really important once we get to large-scale YDP deployments for large MOEs. And then we can do dynamic allocation of prefill and decode nodes. If they're the same parallelism, and maybe our decode nodes are getting overloaded and our prefill nodes are not getting enough utilization, we can just turn a prefill node into a decode node without needing to restart the server or do anything. We just say, you're now going to be a decoder. Set up your scheduler like this, and sort of dynamically manage your scaling within your nodes. Not really scaling in the number of GPUs, but scaling in what those GPUs are doing as an operation for serving your model. Here we have an example of which there's many of like where disag PD shows an improvement over aggregation. This one's actually maybe more interesting than some of the other ones I've shown, where it shows tokens per second per user on the x-axis. This is interactivity. This is what you as a user feel on your request. And tokens per second per GPU, which is like a throughput metric. How much money are you making from these GPUs? And usually, if you're serving like real humans with needs, you want to be more in this middle. You want to like make a good amount of money on your throughput, but you also want to serve at a good enough latency. And so PD really gives you that biggest benefit in that middle ground. It's not going to be something that's giving you, the most money. But if you go for the most money, then you're serving at like 30 tokens per second, which no one's gonna want to pay for that. They want 100, 200 tokens per second. So it really helps you make more money with the same amount of GPUs. I kind of already explained like MOEs a bit earlier. Ultimately, if you don't understand them, you should definitely read about them. But they're ultimately like a really important abstraction that's the future of large language models, for the past year or two. But the key thing they're adding is a form of sparsity with the weights of the model. Each token is only seeing some portion of the weights of the model, and a pretty small portion now, maybe just 10% or 5% for each token. And that really changes how we need to deploy models versus just like a dense llama model as we're scaling up to multi-node inference. And so kind of as I talked about before with YDP, we need to start changing from just tensor parallelism, splitting your large weights across devices. We need to switch to data parallel attention with expert parallelism on the MOEs. And this means we need to start optimizing for sparse all-to-all communication operations rather than just all reduces that we use for tensor parallelism. We need to make sure that the experts that are split now across devices are load balanced in good ways. Because if some GPU has all the experts that are activated on every token, then that GPU is going to be way more utilized than the ones that are maybe just getting a couple tokens per expert. So we need to rebalance these things periodically, and then we need to hide a lot of this communication as the amount of communication increases as we scale to dozens and dozens of GPUs running a single model. And so we introduced EPLB, introduced by the DeepSeek paper. To now work natively with vLLM and LLM-D to periodically improve the balancedness of your experts across GPUs, reshuffling them or replicating heavily used experts across GPU ranks. And even an extension of this is allowing for elastic expert parallelism, where if one of your nodes goes down, you can recover and reshard your experts across the nodes that are remaining without taking down your whole service. Next, another optimization from DeepSeek, we implemented dual batch overlap to break up the single batch of requests we have going through the GPU and breaking this into a micro batch or two mini batches and overlapping so sort of like yellow is microbatch 0, green is microbatch 1, and hiding those operations of doing the compute bound operation of one batch while we're doing the communication operation for the other batch, and hiding these together so we can not get so much of the downsides of this heavy amount of communication we have to introduce for this level of wide expert parallelism. And we implement this within LLM-D with vLLM with the Kubernetes native design by taking advantage of like the leader worker set and like one pod per node. And this works just as well with all the other systems, like defining your custom scores and routers, and abstracting away all your Kubernetes pods. Next, there's KV cache management, which we already talked about. Doing KV cache transfer from your prefill nodes to your decode nodes, or being aware of like your prefix cache that you have in each one of your nodes. But we also can do KV cache offloading with the KV connector. We can offload each node's GPU memory, which has the KV cache, into its local CPU memory as it needs to free up some of the GPU memory. It can also have local storage that it offloads to, and then it can also have remote storage appliances that are shared between multiple nodes to have sort of a global shared KV cache storage if you're getting a lot of similar requests or requests that you need to keep around for a long time, which is especially important for coding agents that are working across large code bases that they're reusing over and over in their prompts, and maybe you step away for an hour and would like to get a good time to first token. And within like the KV cache management, as I sort of mentioned, we're relying on like the KV connector API. We're building more connectors, both into vLLM upstream and also custom ones in the LLM-D project itself, and with custom users for their custom storage appliances and things. And here's this graph is an example of as we do different levels of KV cache storage. Using the vLLM baseline, using a synchronous storage connector, using the LLM-D async storage connector, using CPU memory as an offloading place, using GPU cache as an offloading place, we can get different levels of performance by having these different hierarchical places to store our KV cache. So yeah, those are the well-lit paths of LLM-D, and that's all I've got. Hopefully better with time there.
Yes, we're 15 minutes over, but it's not only Michael's fault. It's mostly Michael's fault, but not only. All right, I'll be super quick. I know there's some stuff waiting for us outside. So if you liked what you heard today, we do pretty much the same thing, not as long. every other Thursday. Sometimes it's every Thursday because there's just so many topics. We call these the bi-weekly vLLM office hours. I know it's unfortunate they happen at 8 o'clock at night this time. If somebody here wants to help and bring these to a more appropriate time in this time zone, we would love to collaborate with you. But Michael and I invite all sorts of companies from NVIDIA to Meta, AMD, many more to join us for an hour every other Thursday and dig deep into a lot of the topics that you heard today, even more. It's also a great place if you have any vLLM questions. That was the original purpose of these office hours. Come, ask. There's always an answer there. You can sign up via a QR code there, or we do record them also. They're all on YouTube, so if you can't really attend at 8 o'clock at night, I know it's challenging, you can always view the recording as well. And then one more minute before we go and eat some food. Please, if you can just take 1 minute right now, I'll pull the Damien demo approach and we'll just be quiet for a minute. If you can just help us answer these 3 questions, that would be very appreciated. I would love to get as many responses as we can now. The easiest thing would be to just give us 5 stars down the line. Just kidding, don't do that, please. Be honest. But I'll also send you this survey link on Monday, most likely, as well as the slides. I know a few people asked for the slides. We'll share those with you as they are. And I believe we were recording today. I don't know how long that takes to get the recordings. Do you guys have any idea how long it takes? Anyways, we'll make sure to also send you the recordings of these sessions while they're ready. And we are streaming our Vienna meetup on Thursday in 2 days. Similar topics, some differences. We'll be digging a lot more into LLM compression and speculators in Vienna in 2 days. That will be on the RedHat YouTube. All right. Oh yeah, GTC conference. This was seen today, but check it out if you want to join us or join NVIDIA. Igor, come say something.
Hey guys, so as part of the NVIDIA, all of the activities that we do, we have the GTC happening. It's free to participate. It's going to be more high level, no technical deep dives, but more like the trends in the general industry. So feel free to drop by. It's all live streamed for the next couple of days. So yeah, you're welcome.
Awesome. Thank you guys so much. Thank you very much for coming. Thanks to our speakers too.